Okay, well, thank you. So today I'm going to talk about some work that was actually done by two students. So really I'm talking about their work. So Vikash Goel and Jameson Wang. And it is about unsupervised video object segmentation for deep reinforcement learning. Okay, before I get started, let me just say a few more words. So as Yao Liang was saying, I am now working as well with Borealis AI. So this is a little bit unusual. So I work half-time for Borealis AI, half-time for the university. So at Borealis AI, I am a principal researcher. And here, Borealis AI is a special research institute that was started 3 years ago and is funded by Royal Bank of Canada. It includes today 5 offices. So there's one in Montreal, Toronto. We've got one here in Waterloo, Edmonton, and Vancouver. It includes as well about 100 researchers. And then what we do is what we would call integrated research. So it's a mix of both fundamental and applied research in the sense that we start from business problems that come from the bank or elsewhere, and therefore there's an applied component. But then as we get familiar with those problems, often we encounter some fundamental issue. We also do the fundamental research. We also publish, just like at the universities. And then in that sense, it's an integrated model. And the type of research that we do is very much focused on machine learning, reinforcement learning, but also natural language processing, computer vision, private AI, fintech in general. So there's a broad range of topics. And then if any of you are interested, so we are going to award some scholarships for graduate students. So the deadline is October 10, and this is the link to apply. Okay, so there's going to be 10 scholarships of $10,000 each, and then they're open to all graduate students who are in artificial intelligence. I should say that for the lab here in Waterloo, it is on campus. We also have a joint reading club of machine learning and finance, and we're going to have the grand opening of the lab later this month. So stay tuned. There's going to be some announcements about that. Okay, so the other half of my time, I'm here as a professor. Some of you sometimes have difficulty finding me, but I am here half of the time. And so as Yao Liang explained, I do work on a number of things. So with my research group, so we do work in deep learning, reinforcement learning, NLP, and theory. Now, I'd love to talk about all of this, but I feel like sometimes talks that are too broad don't have much substance, so I figured I'd focus on just one thing. So one piece of work that I think is exciting, and it's this one here on motion-oriented reinforcement learning. Okay, so here's the outline for the talk. So I'll give you a bit of background about reinforcement learning, and specifically one major issue, data efficiency. We're going to look at one type of solution, self-supervised learning, and then within this framework, I'll tell you about the work that we did in terms of developing some motion-oriented reinforcement learning, which really means here that we're going to do unsupervised learning in the context of images to recognize objects and their motion, and then we're going to feed that to a reinforcement learning agent. This will give it some higher level information that will help in terms of learning a policy faster. So in contrast, most of the work in reinforcement learning that works on images, we just train deep neural networks directly on raw images, and then they have to extract all the features, figure out everything, and that takes some time. So if on the other hand, we can feed in some higher level information like objects, their motion, then perhaps we can do the learning faster. And then so that's what I'll demonstrate here. And so, okay, this work was published at NeurIPS last year, so this is the reference if you're interested and would like to read more about it. Okay, so I'll get started. Now, if you have questions, just feel free to ask me throughout the talk, and let's have some discussions. Okay, so as just a refresher, when I talk about reinforcement learning, is this general framework where we have an agent that executes some actions, it influences the environment, as a result, there are some observations that will be made available to the agent, but also some reward that will tell it how well it's doing. So this is a general framework. It encompasses perhaps some of the most sophisticated problems within machine learning and AI. And then in terms of applications, that includes games, robotics, automated trading, autonomous driving, recommender system, conversational agents, and so on. Okay? So there's lots of applications, but there are challenges, obviously, in terms of making advances in these different applications. Okay, so today I'm going to talk about one very important challenge, which is data efficiency. So for anybody who's worked on reinforcement learning, you've probably noticed that you typically need a lot of data. And then the successes that have gained a lot of attention in the public are in fact all successes that rely on simulated environments. And that's in part because if you have a simulated environment, you can generate as much data as you need. Okay? So more concretely, video games have become quite popular, such as Atari. In robotics, you can use some simulator like Mujoko to train some agents. This is another video game. And then we've got Computer Go. That was also a great success. In all cases, you see there's a simulated environment, and then we can generate as much data as we want. Now, concretely, if I look at Atari baselines, some papers, or in fact many papers, when they report their results, you'll notice that the x-axis is essentially the amount of data, so number of frames that the agent is learning from. And then here I'm showing some plots that come from a paper in 2017 that was essentially just evaluating the state of the art. And in those plots, you'll notice that the x-axis goes from 0 to 40 million frames. So we're talking about 40 million data points, 40 million time steps that the agent had to interact with the environment. Okay, so this is a lot of time steps. And if you think about it, when you play a video game like Atari, most of us, even if we've never played a specific game, if you're given a controller, it will not take you 40 million time steps to get a good policy. You will, explore a little bit, but eventually get a good policy, and it will be much, much shorter than that. So maybe in the thousands of frames, but not in the millions. Okay, so let's have a closer look now at how reinforcement learning is typically done when the environment consists of images. So in video games, then we can feed to our reinforcement learning agent every frame from the video sequence. And then typically what we have is a deep neural network that then will produce one of two things. It will either produce some actions or some values, like Q values. And then based on this, it will then receive a reward. So this is, at a very high level, how pretty much all of the techniques work. And then when we talk about deep reinforcement learning, it means that here, this mapping is achieved by a deep neural network. Okay, so in this picture, there's one thing that should worry you. Okay, so when we look at this, this deep neural network is essentially going to be trained based on the rewards, right? So the rewards are essentially giving us a signal telling us how good the actions are, and then we're going to do some back propagation. So we're going to train all the weights in our neural network based on those rewards. But then how many rewards do we get throughout this interaction? So at every time step, the agent might get 0 or 1 reward. So it's a very sparse signal in the sense that at best, this is one number that has to train millions of parameters here. So we've got a clear imbalance in the sense that we have very little data, very little feedback to train lots of parameters. So here you see deep neural networks typically have in the order of millions of parameters. And now, if you want to train them well, it's normal that you're going to need data of the same order. So that explains why you might need like 40 million frames to train and obtain a good policy. Okay? But and since we get one number per frame, right, then that's why it takes so long to train our neural network. Okay, any questions so far regarding this? Yes?
Is this the reason you need 40 million frames?
Well, so that is one high-level explanation for why it takes so long, why we need so many frames, because yeah, we're going to get at most one number per frame, and then we need data that is more or less on the same order as the number of parameters. Okay, so obviously we don't have a direct mapping, but that is one of the reasons. Yeah.
So you said that you get one number per frame. Isn't that what normally happens? Like loss function evaluating to these one number?
Well, yes, so reinforcement learning is set up in this way where you get a reward at every time step, and unless somehow this is a multi-objective problem where you might get multiple rewards, typically just classic reinforcement learning, you would just get one reward. So at some level, right, we're just following classic reinforcement learning here, and that's the way it is. That's how it's always been, right? But now it forces us to think this through and see if there's something different we could do to train faster, because really if we're just going to get one number per time step, then training millions of parameters obviously will need a lot of those rewards. Yeah?
For the classic deep neural network, which classify, for example, yes and no, we also have one, for example, punishment or for training network. What's the difference here and classic deep neural network training yes and no classification?
Okay. I guess, yeah, he's asking the question of what's the difference between this neural net that is trained based on rewards versus another neural net that would be trained to do classification with yes and no. So yeah, there are differences obviously in terms of architectures. I'll get to this in a moment. So right now I'm just talking at a very high level about how deep neural nets tend to have lots of parameters, and therefore they do need a lot of data. And this is something that was also observed in the context of classification. Like if you have a small data set, a deep neural network often is not as competitive as a support vector machine or other types of models that would have fewer parameters and just better data efficiency. Okay, so yeah, so at that level, there's no difference yet, but we're going to get to the architecture. Okay. All right, so here, let's explore another direction. So this is something that has become popular in computer vision and is now becoming popular as well in reinforcement learning and natural language processing, known as self-supervised learning. So self-supervised learning, the idea is that we're going to train with also some auxiliary task and auxiliary objective. So since we have rewards, and that defines our primary objective, but then there's not enough information in this, perhaps we can have some other task with some other feedback mechanism that will give us additional information, and we can use that to train too. So if we have multiple of those, then perhaps we can train faster. So here you see when you look at reinforcement learning, well, the reward is what we typically use to do the training, but then there's another arrow here, the observation, that provides information back to the network or back to the agent. That's not typically used directly to train, but what if we could use that to define some auxiliary task, some auxiliary objective, and then train maybe the network faster? So classic examples of such auxiliary tasks might be, could we simply have a network that also predicts future observations or rewards? We could also just predict the past ones, or we could do some form of reconstruction, as in an autoencoder. So there's all kinds of things that we could do where we could use essentially these observations as the main driver. Okay, so now if we go back to our reinforcement learning setting, let's say that we want to use the next image to drive the learning faster. So we've seen how things work traditionally in deep reinforcement learning. Now, once we do self-supervised reinforcement learning, then our deep neural network could be used to compute actions and values, but it could also be used to simply predict what the next image is going to be. Now you might say, well, why do we care about predicting the next image? We're just going to get it at the next time step. Sure, but the point is a reinforcement learning agent is trying to select actions that are going to allow it to perform well in the game. And if it can predict what's going to happen in the game, then that helps in terms of choosing those actions. Right? So it's a natural thing that is useful. If you're going to play a game well, then implicitly you should have some way of anticipating what's going to happen in that game. Right? So then we can define an auxiliary task where now if we're predicting the next image is a dense signal because how many pixels do we have in an image? We have on the order of millions of pixels. So now we have millions of signals that can train millions of parameters here, and therefore we're going to be able to do it much faster, or at least we're going to be able to get the network into a state where even though that will be mostly for predicting the next image, that's still useful information that will help for computing actions and values. Yeah?
What happens in the next step? Should it not depend on what the agent actually does before the next step?
Yes, okay, so the question, yes, wouldn't the next image depend on the action of the agent? Yeah, so yes, it does depend, and then the agent is trying to figure out which action to select, but still, in that process of selecting actions, right, if it can predict what's going to be the outcome of every single action, then it's already a good first step towards planning, right? If you can't even predict that, how can you select your actions well, right? So in that sense, it is useful. Yeah.
With this new additional information, you need some representation of the model of deep learning, right? So it should be, for example, you have to know the dynamics or predict, like estimated with some other neural network. So in that case, can you again use model 3 reinforcement learning algorithms, or it should be only model-based?
Yeah, okay, good point. So here the question is, yeah, should we have a model-based or model-free technique? Simply because if we can predict the next image, at some level we are building a model, and will this lead to just model-based techniques? So I'll show you how what I'm going to propose will be useful in both model-based and model-free. So just hang on for a moment. Okay. All right, so another aspect that is important in terms of being able to come up with a good strategy is when we play some games, as humans, if you look at those games, and perhaps it might be the first time that you see those games, right, then what do you see? Right? So if you look at Sequest, you'll see immediately that, okay, there's like a submarine shooting around, and then it's shooting potentially, I guess, some monsters, some swimmers, and so on. And that's something we can immediately understand just by looking at the game and based on our prior knowledge, right? For Space Invaders, we immediately understand that, okay, this must be our agent, there's some monsters here, and we're shooting them, right? And then in this game Breakout, we immediately understand that there's a paddle, there's a ball that we hit, and then the ball will make some holes in the ceiling, right? So we understand these games, and then so as humans, we have an advantage because we can immediately start planning, right? But now, if we consider a reinforcement learning agent, what the reinforcement learning agent is fed with, which is a frame, same as a human, it really receives a sequence of pixels, and then the first thing it has to do is understand what's the meaning of those pixels. In other words, extract useful information. So this is another big difference. So beyond the fact that the reward signal might be sparse, there's also a question of how is the information processed, and can we get a computer to a level that would be similar to what humans do when they start playing, even if they've never seen this game before, right? Because as humans, we end up recognizing objects easily, and then we can also tell that often the moving objects are the important ones in games. So we start planning immediately based on this, whereas for reinforcement learning, the agent receives a frame, but it's really a sequence of pixels, so that means a sequence of numbers. And if instead, you were asked to play these games, and I was just going to show you a long vector of numbers, that would be a much harder way to play the game, right? So now you'd understand what it feels like to be a reinforcement learning agent. Okay, so in any case, the question will be, can we change this so that the reinforcement learning agent can also work with higher level information like objects and also their motion? Okay, so if we go back to our classic framework for deep reinforcement learning, this deep neural network, the way we can understand it at a high level is that it really is doing two things. So the bottom layers of the deep neural network typically do some form of feature extraction. And then the top part is typically doing what is needed for the task. In this case, if it's selecting actions or computing some values, this is really about, I guess, coming up with a policy. So the top part is really responsible for the policy optimization. So in other words, the neural network here is doing two things simultaneously. It's learning to extract information from images, and then it's learning to select actions, in other words, to optimize its policy. What humans typically just have to do is the second part, just the policy optimization part, because for us the feature extraction is fairly immediate, right? So here the question will be, what can we do to essentially make it easier as well for the computer to do the feature extraction? Okay, so to do this, what I'm going to propose in the next few slides is an approach that will allow us to pre-train our network so that it can recognize objects and their motion, so that then the reinforcement learning agent can just focus on the policy optimization. It doesn't have to spend a lot of time just understanding what all those pixels mean. Okay, and this leads to the work that we call motion-oriented reinforcement learning. And that's going to be because what we're going to learn is essentially to recognize those objects, specifically the ones that are moving, as well as their motion. So in many games, this is what matters, and I would argue that in dynamic environments, that might be a good heuristic in general. Things that are moving tend to be more important than things that are not. Okay, so the approach will work as follows. So we're going to have two phases. So in phase one, we're going to do unsupervised object segmentation. And then here, we're going to do this by using only 1% of the frames. And then in this phase, we're going to execute random actions. So our agent is going to be dropped into an Atari game, just like what we saw in the videos before. And then it's going to execute some random actions. It doesn't matter. It's not going to do anything sophisticated here. But its goal is just going to be to learn to segment objects and also recognize their motion. Once this is done, then we can use those objects and their motion and feed that to the policy network that will then come up with policies faster. Okay, so we're going to have those two phases. And then the beauty is that phase one, to get this higher level information, we're just going to use 1% of the frame, so it's going to be negligible in a sense. Okay, so the approach here is going to leverage some things that have been well known in computer vision for a long time. So if you want to segment objects, and you do this in a supervised way, then it is labor intensive to obtain labels for every single pixel. So for instance here, there's a scene, and if I want to distinguish the cars versus the building versus the street versus a pole versus people, right? So I could have different classes, and then the problem here is to get a predictor that can label every single pixel correctly. But then to obtain this ground truth, if we ask somebody to provide the labeling, obviously this is very time consuming because there's so many pixels to label. An alternative is to use other information. For instance, if instead of just having a single image, we have a video sequence, and then in that video sequence, the things that we care about are moving, then we can leverage optical flow, and in fact, leverage all the work on structure from motion to get a sense of where those objects are. So here, for instance, if we just compute the flow of a person biking and some people walking, then we get a sense already of their location, and then we could get a rough segmentation. Same thing here for somebody playing tennis. Okay, so a few years ago, there was a paper, in fact, there were several papers put out on arXiv by different research groups about how to do unsupervised segmentation from video sequences using some deep neural networks. And this is one example. So this one is known as structure from motion network, so SFMNet. And then in this network, there's two parts. There's a part here that will estimate the motion. So in other words, we've got a pair of frames. And then from this pair of frames, we compute some embedding using some convolutional layers. From this, we compute some object motion. So in other words, what would be the direction and then the motion of every single pixel in the image. And then same thing for the camera. So sometimes what we observe could be explained not so much by objects in the scenes that are moving, but the camera itself. So it might be camera motion. And then altogether, this will eventually allow us to compute the flow. Okay, so the goal of the top network is to compute the flow. Now, if we're in a 3D environment, it helps to also know depth information. So then the bottom part is going to compute depth information. From this, compute a point cloud. And then that helps in terms of computing some better estimates of the flow. Now, once we have the flow, the idea is that we can take our first frame, add the flow, and get an estimate of the second frame. And now we can compare that estimate of the second frame to our true second frame. The difference then can be used to backpropagate through this entire network. And then this network naturally evolves in a way where it will figure out what is the motion of objects and cameras, as well as the location of the objects, so object masks here, and also the depth information. So all of this tends to eventually be learned reasonably well. Okay, any questions regarding this network? Yes? Yeah, very good point. So here, I guess, yeah, the question is, how do we know that what I've labeled here, camera motion, object motion, is really camera motion and object motion? Because, I mean, these are just things that are intermediate vectors being computed in this entire network, right? And then from that perspective, I mean, it could just be computing something else that does not correspond to camera or object motion, right? So here, yeah, this is, I guess you can think of this as there's some, the structure pretty much forces the computer to compute something that can be interpreted as camera motion, because here, if we interpret these numbers as a camera motion, and same thing for object motion, then when we compute, so we can use those to compute a transform point cloud. So there's some specific transformations associated based on that. And then naturally, if it manages to compute the flow correctly, it will be very hard, given this structure, for it to compute something else that cannot be interpreted as camera or object motion. So this is a case where, yes, we have some hidden variables, but then you could think of this network as implicitly encoding a whole bunch of constraints. We've got some hidden variables. We're finding values of those hidden variables, but then those constraints implied by the structure don't leave much room for the network, and then it has to more or less come up with numbers that can be interpreted as labeled here. Now, this is what we observe empirically. We don't have proofs for such things, but that's what tends to happen empirically. Yeah?
And the second network is a single frame that outputs depth image. Why is it not feature extraction? There's nothing specific to depth.
Yeah, that's a good point. So how can you compute depth from just a single frame? So, okay, there's a whole literature on trying to do that. And obviously, it's not the best setting, so it should be using more frames. But that's what was proposed in this particular network in 2017. Okay, so I would argue that, yeah, it's not necessarily the best network, but that's just one example. And here we could try all kinds of variants where we could feed in more frames. And in fact, we could argue that some of the information of the top network should also help in terms of inferring depth. So yeah, so there's many other ways that I would think should be better as well. Yeah. Oh, I see. OK, so yeah, so I guess there is a course where this is being taught, so it is possible, OK, to do it from a single image. Good.
Well, I mean, and the question is, like, how is this depth? Like, why is it not featured? So over here, how are you using the depth to get your predict the next frame?
Well, so you see, when we compute flow information, if we don't have depth, then it is hard because, I mean, we live in a 3D world, right? And the idea is that the next image is just going to be a 2D representation, but then, you know, the location of the pixels and so on depends on I guess, the distance of the objects. So that's why really we need the depth information ideally to get a good representation. Okay. Yeah.
So the output of the whole network, the architecture is the optical flow, right?
Yeah, the output of the whole network is optical flow. And then the idea is that we can use this plus the first frame to compute an estimate of the second frame, and then compare that to the ground truth second frame and backpropagate all the way through.
Right. What is the output instruction? Like, how's the loss calculated for the instruction?
So the loss is simply, I guess, measuring Euclidean distance between the predicted second frame and the exact second frame. Yeah. OK, so this work, again, was done in 2017 at Google. They applied this to some scenes looking at monitoring cars at intersections. And so we've got some examples of the results that they obtained. So here, they highlight the predicted motion mask and the ground truth motion mask. So essentially, in those scenes, cars or vehicles are the main things that are moving. So that's what they're hoping to recognize. So you can see that it's doing quite well on those. And we've got here the predicted flow as well as the ground truth flow. Now, at the bottom, we've got two examples where it did not perform well, so where there are major problems. Okay, so this technique is not perfect, but it gives you a sense of how well it works in general. Okay, so in our case, what we did is we adapted this to Atari Games. In fact, here we simplified the network because for Atari Games, it's a 2D environment. There's no depth information. There's nothing 3D in there, so it's simpler. And then our goal was to then plug this into a reinforcement learning agent. So, okay, so here we essentially have the top part of the network that I showed just before. So SFMNet has two parts, right? The top part is the one responsible for computing object mask as well as motion. The bottom part is the depth. But if we're in a 2D environment, we don't need depth information, so we're just going to get rid of the bottom part. Okay, so that's what we did. And otherwise, the network is very similar. But we did do some additional modifications. So first, we removed all of the skip connections. So if you go back again, this network has a bunch of skip connections. we did not want to have skip connections because we'll see in a moment that we want to be able to treat this embedding here as a compressed representation of all the information that came from the two frames. And then we want to make sure that in here we also have all the information we need to compute camera and object motion. So then it was important for us to not have any skip connections, because otherwise some of that information could be computed through some other paths in the network. Okay. We also changed the reconstruction loss. So just looking at Euclidean distance is not a good thing in the context of images. So instead, we use a structural dissimilarity. We also did some flow regularization. So we use an L1 loss for this. This helped us to make sure that our object masks tend to be small, because otherwise, if you want to get a segmentation, it is important that you perhaps get just the objects or just the pixels that are moving. And then without this, it would tend to come up with objects that are bigger, and the boundaries would not be as good. And finally, we did the training by curriculum learning. So we combined the two losses, so the reconstruction loss plus the regularization. And then we simply increased the regularization from 0 to 1. Yeah?
You said flow regularization, so flow means like the motion flow, right? I'm not sure how you relate this to the size of objects.
Yes, so...
I mean, I understand the formula, but I don't need to understand it. Just like flow regularization means like regularization of motion. When you talk about size of objects, I couldn't connect.
Yes, so I guess it's best to look at this formula. So we've got the mask. This is the translation. And then so here,
So translation is the motion.
yeah, translation is the motion. And the idea is that we want to obtain some representation where we would infer as little motion as possible to explain the second, yeah. So that's why here we multiply by the mask. Okay, so every mask is in principle corresponding to an object and therefore has a single translation. But now if we want to make sure that our object masks are not too large, then it turned out that it was better for us to put the L1 regularization over the motion of each one of the pixels in that mask as opposed to on the mask directly.
The reason I ask my question is typically flow regularization becomes so because also having consistency of your dense vector field.
Okay.
Rather than you have kind of a discrete, so it's different.
Yeah. So I think, okay, yeah. So yeah, perhaps I'm not using the standard terms from the literature for this. Differently, okay. Okay. All right, so yeah, these are some of the changes that we did, and we'll see in a moment that they were essential to obtain good results. Okay, so now we applied this to Atari Games. Concretely, we fed in pairs of frames as input. Then we have our convolutional layers. From this, we compute object and camera translation. So this is our motion. And then eventually, we get object mask and also optical flow. So for the object mask, we can simply display them here. So this column here is the sum of all the masks. This one is simply looking at the most salient or most important mask. And then here we've got the optical flow for all of the masks. Okay, so you can see that for breakout, there's a paddle, there's a ball, and then these are the things that are moving. So as expected, that's what it recognizes. And then you can see as well that it has a different motion for the ball versus the paddle. Okay. For Pong, same thing. We've got now 2 paddles, 1 ball. That's what is being recognized. Now you'll notice that these segmentations are not great. Okay. So by computer vision standards, right? So if we talk about object segmentation, I mean these are really, really, really rough segmentation. But the point is that I'm not interested in segmentation for the sake of segmentation. I'm just interested in getting high-level information I can feed to a reinforcement learning agent. So in the same way that when you drive a car, and you look at obstacles as you drive, you don't have precise knowledge in your mind about the exact distance of every obstacle. You just know roughly where they are, and you can drive effectively. So here for reinforcement learning, we just need to have some rough idea of the location of the objects, their motion, and so on. And what I'm arguing is that this is going to be good enough. OK, so I've got more examples on 3 more games. We actually did this on all 59 games within the Atari set. So it worked out well for Sequest as well as Space Invaders. Space Invaders is interesting because there's a bunch of monsters, and they all move with the same motion. And here what happens is that we have a fixed number of objects that can be recognized, and what's tempting is to hope that it would associate each monster with a single object or a single mask. But because they all have the same motion, then it tends to essentially group them together as one object. And here we did not impose any constraint that would force the objects to be contiguous, right? So essentially the objects could correspond to different patches of pixels in different parts of the image. And that's exactly what happened here. OK, the last one, Beam Rider, is very interesting because this is a game where you have some vertical lines that are beams that are essentially flowing down on the screen as you play. But these are just visual effects that have no impact on the game whatsoever. So our technique, in a sense, did what it was expected to do. So it recognized those lines as moving because they're flowing down. However, we're going to see in a moment that because this is not useful for the game, now it's going to be feeding uninformative objects to the reinforcement learning agent, and in fact this won't help, and it will hurt. Okay, so this is an example of a game where we're going to do worse as a result. Okay, so I've explained now how we do the object recognition and the motion. Next, we need to plug this into a reinforcement learning agent. So what I've done is that I've depicted here what would be a classic deep reinforcement learning agent, and I've added one connection to the top part that is responsible for computing object mask and motion. And this link is essentially the link that will feed high-level information to my reinforcement learning agent. So here, this is a classic deep reinforcement learning agent in the sense that it has a bunch of convolutional layers that process images. And then typically, there will be some dense vector that is then fed to an actor and potentially a critique as well. So if you have an actor critique reinforcement learning technique, you would have those 2 boxes. If you just do Q-learning, you would have a single box. But the point is that there is one vector like this that comes from processing the image that is fed to the reinforcement learning agent. Okay, so this is just a generic architecture that you could argue, is representative of pretty much all the reinforcement learning techniques. Yeah.
So I'm just curious, why do you think you need like this lower part with the input and the place where you concatenate? So that I guess the motivation is the first part is that the optical flow helps the network to learn what's moving and so on. But then the lower path tells you that there's something else besides moving objects is important.
Yes, very good point. So yeah, so the question is, why do we need the bottom part? Because my whole talk was about coming up with object mask and so on. We're feeding this in, so really we should not need the bottom part. The answer is that here, the top part is recognizing objects that are moving. And now in some games, there will be other information of objects that are not moving or other things that are going to be important. And then so the bottom part is still useful to capture that. So initially, we did try just the top part, got some good results on some games, but some terrible results on other games. And then the idea is that if there is still some information that needs to be extracted from the raw pixels, you still want to have this ability to do it. And that's why we keep the bottom part here. Yeah. OK, so, and yeah, the other interesting thing to notice is that what we're feeding in which is a fully connected layer of size 512. This is really, I guess, an embedding of the object mask and their motion. Initially, we tried feeding in directly the precise representation for the object mask and the motion, but that did not work as well as just feeding in an embedding of that. Okay? And we believe that this has to do just with the optimization, that perhaps here, when you use just a dense representation like this, there tends to be some redundancy. It's higher dimensional and so on. And then there's more flexibility. So if the optimization gets stuck into a local optimum, then there's, well, I guess here there's less chance that it might get stuck into a local optimum. That's our guess. But it's really something empirical. And other people have noticed the same thing, that often it's better to just feed some dense representation of whatever you're interested in when you do the optimization with deep neural networks. OK, any questions regarding this? Good? Yeah, OK, one question. Uh-huh.
The green and red output, is there any difference?
Yes, OK, so yeah, so here the flow is color-coded. So I don't remember which direction is green and which direction is red, but the idea is that, yeah, you could have motion in different directions, and then the colors are used to capture that. OK, so this was architecture, and essentially you see this part, which is the classic reinforcement learning part. We can have any architecture. So we tried some of the popular baselines. So A2C and PPO are two popular baselines. And really, we could plug in anything. And now we did a comparison between what if you just have a regular reinforcement learning technique that would just be the bottom part, versus having the top part with this link here that essentially feeds in additional information. So when we did this comparison between our augmented version versus just the baseline with A2C, we ended up doing better on 26 games, about the same on 30 games, and worse on 3 games. With PPO, we were better on 25, similar on 25, and worse on 9 games. OK, so I've got some videos here that illustrate what happened in 4 games. So for Pong, Breakout, Sequest, everything worked out nicely. You can see in the left-hand side the classic view when you play the game. On the right-hand side, you can see the object mask in real time, as well as the motion. So this helps us to understand whether the network is segmenting the right objects, capturing the right information, and being able to interpret better what might happen as a result with the reinforcement learning agent. So yeah, so you can see for Breakout Pong, it's doing the right thing. For Sequest as well. Even though Sequest, you can see that the object masks are very rough, it's still capturing the right information, and as a result, it does well. For Beam Rider, it's doing what it's expected, but again, it's capturing those horizontal lines that are actually completely irrelevant in the game. And what it should be really focusing on is to capture these little monsters that are dropping and also the bullets that are being shot. But these bullets and monsters are so small compared to the rest that right now we're not capturing that. Okay, so essentially here we're going to be feeding to the reinforcement learning agent irrelevant information. So that's an example of a game where things don't go well. OK, so we did a comparison between, so this is some curves for A2C. We did it as well with PPO on all 59 games, but I'm just showing you the 4 examples for the 4 videos. Our approach is in yellow, and here the idea is that you want to get higher rewards as fast as possible. So here the x-axis goes up to 10 million frames, so that's already better than 40 million frames. And then our approach tends to find a good policy faster than the baselines. Okay, so yeah, we've got different variants of the baselines as well. I'm not going to go into details, but yeah, the main message is that we find a good policy faster. We don't necessarily find a better policy. It's just that we find an optimal or otherwise what is considered the state-of-the-art policy for each game faster than the other techniques. Beam Rider is an exception, so you can see that yellow, which is our technique, does not perform well at all. Okay? Any questions regarding this? Yeah?
In one previous slide, you compared two baseline. You said 25 games better.
Mm-hmm. Yeah.
But here you say it's finding the same quality of policy, but just finding faster. So is it better? Or?
Oh, okay. So yeah, when I said better, yeah, what I really meant is that we find state-of-the-art policies faster. Yeah. Okay. We also did an ablation study. So for the network that does structure from motion, so here, as I explained, there was some curriculum learning. We used an L1 loss. There was flow regularization. So if we remove some of these things, an interesting question is, do we do as well or not? And what this ablation study shows is that we really did need to do all of those modifications. So they do make a difference. So our full technique, which is in blue, right, performs better than if we don't use curriculum, if we don't have the L1 loss, and if we don't use flow regularization. Okay, so this is what I wanted to present today. The main message, again, is that if we want to speed up reinforcement learning, often it's a good thing to try to find some auxiliary task. Like in this case, we use the next frame to essentially learn to segment and also find the motion of objects, which gives us higher level information. And then it also helps in terms of interpretation. And so overall, this was something quite good. Now, in terms of future work, obviously, we'd like to extend this to 3D environments. Now, I thought this would not be too hard because the original network was for 3D, but so far I've had several students take a crack at this and not really succeeding. So in any case, this is something that should be doable. Another interesting direction is to learn a model-based approach. So learn a model and then have some physics-based dynamics. Because once you can predict next frames and also the motion of the objects, right, then you could leverage this into your planning. We're not doing this right now, but you could have a physics-based model, like in Pong, for instance. You hit the ball, then we know from the physics what should happen in terms of its motion for some time until it hits something else and so on. So we should be able to leverage that as well. There's also a line of work in reinforcement learning called object-oriented reinforcement learning. So for more than a decade, people have been exploring the idea that perhaps we should do reinforcement learning on objects as opposed to low-level features. But in that entire line of work, the assumption was always, well, someday somebody is going to be able to give us the objects. For now, we'll just assume that we have them. And we've essentially filled in that gap. So now we have a way of extracting the objects. And now it would be interesting to go back, revisit this entire line of work, and make it practical. Now, if you're not interested in video games, and you might ask, okay, what is useful in life? So where could this be used? So it could be interesting for unsupervised vehicle tracking. In fact, that's what this SFMNet was designed for in the first place. And then we could we could use reinforcement learning for traffic control. So this is an interesting direction in terms of real-life application for this work. Okay, and we've got, again, the reference here. So I'll stop here. I'll take any further questions. Okay. Yeah.
So thanks for the talk first. Also, can you go back to the slide where you're showing examples where it worked and just make one? Yeah.
This one, okay.
So you said like with the line, with the game where there are like lines go, yeah, on the right.
So yeah, I'm not sure why it's not working right now. Let's see. Okay. Yeah. So on the right, okay, so beam rider, yeah?
So I'm just trying to say, like you said, it doesn't work very well, and I mean, this reason is it just can't separate what's important from what's not important. So this is where kind of needs, besides motion, it needs to try to learn from that motion, like some kind of categories, and it's probably very hard to do in an unsupervised manner. So I mean, I'm not even asking a question, more like, would be, I mean, that would be an interesting thing to try to do in an unsupervised manner, to learn relevant classes versus unrelevant classes without any labeling.
Yes, very good question. Yeah, okay, so the question is, could we learn categories of relevant versus irrelevant objects? And in fact, at some point we thought we had a way of doing this through attention mechanisms in deep learning. So we thought that, okay, we're going to have our reinforcement learning agent that essentially learning to maximize rewards, and then we'll just have an attention mechanism in there that will learn over time which objects are most relevant or not. But for some reason, it just wasn't working out. But yeah, conceptually, I think it's doable because we can use a reinforcement learning signal to do this type of learning. But yeah, we haven't succeeded.
I just like this problem because, like, that's a hard problem, like learning without supervision at all. And I'm sure you're making steps in this direction, but just like this one more step.
Yeah, absolutely. Yeah. So this is really what's important here, because at the end of the day, yeah, it's one thing to be able to recognize everything in your environment, but usually when there's a task, there's a few things that matter, and so you want to recognize those and do it in an unsupervised way. At least here, in the case of reinforcement learning, the task is defined by the rewards, and I think this is where this signal should help us identify that part. Yeah. Yeah?
I was just wondering which optimization methods you use if you have to do anything special for the L1 loss, and how big the computers are that you need to do the training for this.
Okay, so for the optimization here, the students essentially were working in TensorFlow, used some of the optimizers that were part of TensorFlow. They're all gradient-based. And here, I don't remember, it must be written in our paper which one. I'm going to guess it might have been Adam, Adagrad, RMS Prop, or one of those optimizers. Okay, so there is definitely room here to do better optimization. In fact, one could argue that this is the crux here in deep learning. So often architectures are designed in a way to help the optimization. So if we had better optimization, then a lot of the architectures might look very different, or it would be a lot easier to design. And then for your other question of what computers did we use, so here we were leveraging GPUs, and then in fact, yeah, we ended up renting machines on Amazon because we just didn't have enough GPUs. So yeah, so to do these 59 Atari games, so for each one of them, the training, the computation, the evaluation, and so on was several hours to a day, and we had to do this 59 times. So we parallelized that in the cloud. Yeah. Yeah.
So you had briefly mentioned something about agents taking an action. Let's say the agent has a choice of 4 actions, and for each action, the agent can actually know what the outcome is going to be, like some predictability of that. So somehow I guess the algorithm, where is that predictability coming in? Is this algorithm that you're is there a predictability of the agent in terms of something similar to what you do in research, where you can roll out a few steps?
Okay, so you're asking essentially how is the agent learning to pick good actions, and what's the signal helping it to do that? Is that right?
So is there a roll forward mechanism somewhere in the agent, or is it just using the features from the videos, just like we normally do?
Well, so here, I mean, it was the rewards. That's the main signal, right? Obviously, we also had the auxiliary task to train the top network, but then you see the reward was essentially responsible for training the bottom part. And then here, you see it depends on which framework we work with. So if we're using A2C, it's an actor critique. PPO is another actor critique. We could have used Q-learning as well, but that's not really the state of the art anymore, right? So, so then I guess in all these frameworks, I mean, at the end of the day, there's some loss function, and then you simply optimize that using some gradient-based technique.
You mentioned sparse rewards, right?
Yeah.
Yeah. So when you said sparse rewards, I thought like it was more something like a delayed reward setting, where you don't have signals every time, and then you maybe just get a signal at the end of the game. And
Right.
was that what you mentioned, or was it like just sparse?
Yeah, okay, so sparse rewards here, I was using it mostly to mean that we're simply getting one number per time step. But you're absolutely right that, okay, that doesn't make it sparse in a sense. It's still dense with respect to time. But in terms of information overall, it's very little information. That's what I meant to convey. There is also obviously the case where, let's say we play the game of Go, and maybe our reward is just whether we win or lose at the end. Then we would have sparse rewards in the sense that most time steps we would have nothing, and then just at the end we would have a reward. So that's an extreme setting of sparse rewards. But even if you get a reward at every time step, the argument is that this is still not enough. Like, you can't train with that to obtain good neural networks that have millions of parameters. Yeah. So your question is, what is the ratio between the auxiliary task?
How much was the loss of the auxiliary contributing to overall?
Okay, so yeah, so in this network, you see the auxiliary task is the top network. And then, so we are using the auxiliary task only to train the top part, okay? And then the reward is the main task, and then it's responsible for training the bottom part, but also a little bit the top part, okay? So here we were using both of them simultaneously for training, and then it's just this part of the network that gets trained by both of them simultaneously, okay? Okay, I don't remember the details. I'm guessing that, yeah, we were probably just taking a step in the direction of the gradient with respect to each loss function at, every time step, and then so therefore it must have been equal. Yeah.
It's possible that you have the motion of the lines detected from this part is just the same.
Yes, that's a very good point. So I guess for Beam Rider, the network ended up recognizing those lines that are moving, and then since the auxiliary task has a lot more, has a dense signal, a lot more information, then that would dominate naturally, and therefore it's going to work hard to recognize that these moving lines, right? But I guess your point is that in this case, it should have been the reward function here that trains this to eventually recognize that those moving lines are irrelevant, right? Yeah. Yeah, that's a very good point. So I guess we didn't do that. So well, at some point, we did do training in, like I said, phase 1, where we just train this part, then we freeze it, and then we just train the bottom part. The problem with doing this is that the top part is trained just with random actions for the first 1% of the frames. But then in some games, when you move from one level to the next, right? Or let's say that you simply go further into the game by eventually executing good actions, then there might be new types of objects that need to be recognized and so on. So then it's important to continue training with the top part as well. So yeah, but you've got a point that here there's contention between these two regimes, and it would be nice to have a way to make them work together as opposed to against each other. Okay. Oh, yes.
The Ablation Study. The target
Um,
Is the lowest
yes.
that contributes the most to the architecture?
Right. Okay. So yeah. So at least the way this is displayed, it does suggest indeed that no curriculum is the thing that was hurting the most. However, I'm not sure if this is just an artifact of our legend, because I believe what we did was more like an ablation study where there was the full technique, then we remove flow regularization, then on top of that we remove L1 dust, then on top of that we did no curriculum learning. So I have to check the paper again for that.
Now that's interesting. The curriculum can contribute the most to the education.
Yeah. So yeah, it does look like the curriculum is very important in that sense. Yeah. Well, at least okay. It's clearly among the things that would get the worst if we don't do curriculum. Here, there's something else that's worse. So the orange part, so that would be no flow regularization, and same thing here. So.
I want to know, like, what is the, I mean, if the curriculum did contribute the most, what is the intuition behind it being the most contributing factor?
Yeah, that's a good question. So, okay, curriculum learning is often used when you need your network to essentially kind of gradually learn certain concepts so that then it can perform well on the harder tasks, right? So you train it with some gradually, with some tasks that are increasing in terms of difficulty. And so if I just go back, yeah, so here you see what we changed was to go from no regularization to having an important regularizer. So the idea is that you see, without regularization, then we're not forcing the network to find necessarily small object mass. We're just saying, okay, try to reconstruct the next image, right? And then if the object masks are large and if the flow information is more than it needs to be, then it's going to be okay. But then after that, we tell it now, try to minimize that. So it kind of makes sense from this perspective that this is sort of like an intermediate step that's easier, and curriculum learning lends itself well for that.
It's like, okay, learn the maths first and then try to predict the flow.
No, so it's more, you see, like with an L1 regularization, the idea is that you want to make some of these things zero as much as possible. So if you don't need to have a mask, don't use one. So use as few masks as possible and masks that are as small as possible. That's the effect. Yeah.
Okay, so you have more questions, we will ask Pascal.
Okay.